Welcome to this talk on joint communication sensing, which is a winning combination for 6G. My name is Noll Barreto. I have just recently joined Nokia, more precisely in September last year. The previous 4 years, I was working with the Barkhausen Institute in Germany, in Dresden, which means that this is not necessarily Nokia's vision for joint communication sensing. No, it's my personal vision. So some of the things are from Nokia, most of them are not. So just a second. Okay, so when we talk about 6G, what's really going to be new in the next generation of wireless communication? Right? We can think of many different things that will be new. We'll have many new features, which are mostly evolutions of what we already have now in 5G. But when you think about what's going to be really new, we can say that's the merging of different domains. Right? So previous generations up to 5G were most concerned about the internet, right? About providing wireless internet. But in 6G, we think that this will change. We will see a merging of the cyber world, of the internet, with the real world, with the physical world, with many sensors and actuators and machines and robots and drones and whatever. We have virtual reality, extended reality. And all this will only be possible if we have machine learning, if we have intelligence. Right, so that's the vision for 6G, and that will be fundamentally different from previous generations. Again, it's not only about data, it's about the real world. I mean, the stakes are higher because of that, right? We'll have the internet controlling our cars, controlling robots, so things really have to work very well with security, with reliability. And one thing that we'll need is sensors. We have to sense the environment. Right? We have to be able to map the environment and detect objects correctly. And for that, we have sensing integrated in the future networks. So that's why, again, we have sensing. So why communication and sensing? Why do we want to have both together? Of course, we all know that both radar and wireless communications rely on the same physical principle, which is the propagation of electromagnetic waves. So every time we are communicating, say a car is communicating with the base station wirelessly, part of the signal will be reflected by objects in the environment, for instance, by people in the environment. And we could use this reflection also to perform radar sensing. Right? And when we have both together, we can see that communication systems can benefit from sensing. For instance, there are some works which propose improved beam allocation. Once we know where the obstacles are, once we know our environment, we can use that to analyze the context to increase security of cyber systems. And on the other hand, I mean, radar sensing can also benefit from communications. We can coordinate interference, which is becoming a serious problem in radar systems. We can perform sensor fusion to combine the results from several different radar sensors centrally and improve the sensing by this. So we can clearly see that there are benefits from having both things. But why do we need them to be joint? I mean, we already have communication systems, we already have radar systems, they are widely available, right? But right now they are performed separately. We have different systems using different parts of the spectrum, using different hardware. So why do we need to do them jointly? Why do we need joint communication and sensing? And there are several reasons to do that. One of them, of course, is efficiency. We have limited spectrum, so we should reuse the radar spectrum for communication and vice versa. So it makes the spectral usage much more efficient if we can allocate the resources according to demands. We can also reuse the hardware. I have one single hardware which will be used for both communication and sensing. That will probably allow the hardware to have a small form factor and be more energy efficient. I say probably because this is still a point which is not clear. I mean, hardware can be quite complex thing, and radar and communications that have some differences, but that's the expectation. And most of all, we'll have flexibility. Again, we can dynamically allocate the radar resources either to communications or to sensing depending on the needs. So we see that in 6G, we will offer radar as a service. We have already now many different services in wireless communication systems. We have broadband communications, we have localization, we have ultra reliable low latency communications. And on top of that, we can also have radar sensing in future systems. And again, what's important here is they have different requirements at different times and places. And one simple example is when we are, for instance, in a highway, we have many cars using radars. So we have a very large need for radar sensing. They will, of course, also communicate, but the primary usage there will be for radar. But when we are at home, we want to have broadband wireless communications to watch a video or to play some video games using virtual reality. So we need this bandwidth for data communications. So the needs can be widely different in different places and even at different times. So by allocating resources flexibly, we can accommodate those different needs. Okay. So that's the idea. Why do we need it jointly? First, to have more efficiency, the user spectrum usage and power usage, and also to have flexibility to allocate resources according to the needs. And one figure just to show the spectrum issue, how serious it is. If you look into cellular communications in 5G, right now we have about 1 gigahertz of spectrum for 5G. If we also consider millimeter waves, which is currently hardly ever used, we would have maybe 2.5 gigahertz of spectrum for wireless communication. And this spectrum is used by 91% of the world population. I mean, nearly everyone all over the world has access to cellular communications. That means that we really have to squeeze as much as we can from this spectrum, which is not widely available. So we are designing 5G to provide a spectral efficiency of over 20 bits per second per hertz, which is quite challenging, right? Because again, we have a limited spectrum. You really have to make the best use of it. Whereas for radar, currently we have the frequency band located in Europe in the 77 gigahertz band, 77 to 82. So we have 5 gigahertz of band just for commercial radar, not even including military radar and weather radar, other different types of radar, just for commercial radar, which is currently used in most for automotive applications. Right, and we have maybe 1% of the world population which have cars which have radars. And this 1% of the population has access to 5 gigahertz, 5 times more than for cellular communications. And if we, I mean, sorry to talk about spectral efficiency, I want to talk about radar, but if we sort of measure the amount of information that's provided by detection, we would come with something in this order of magnitude, 2 to 10 to the minus 7 bits per second per hertz. So we mean that means that this part of the spectrum is used with a very low efficiency, whereas we have to squeeze as much as we can from this part of the spectrum. So in a sense, this is not fair. I mean, there are reasons why we need that large bandwidth for radars. We need the resolution, but even then, it's not very efficient. I mean, there are no standards. Anyone can do whatever wants. There's no coordination, so it doesn't really work very well. Okay, so we can see, okay, we need joint communication sensing, I mean, to have more flexibility, allocate the spectrum more efficiently, but also we need enablers. And so why are we talking about this now? I mean, spectrum has always been an issue, but why now? Now there are also some technological and economical enablers for that. First of all, we see that signal processing for radar and for communications is converging, right? So we can observe that communication systems, they are dealing with ever larger bandwidths and in higher frequency bands, which is similar to radar. I mean, again, as we have seen, radar, we have 5 gigahertz. I mean, so the spectrum is quite large. And yeah, wireless communication systems are also evolving. In 5G, we have 100 megahertz. In 6G, you probably have 400 megahertz bandwidth, perhaps even more. Radar signals have so far been processed mostly analogically. I mean, partly analogically and part digitally. That's what we see right now with radar systems. But we can see an increasing digitalization also of radar signal processing, which makes it closer to what we do now in communications. And also in radar, we usually have narrower beams so that we can really focus on the object that we are detecting and concentrate energy. We also see something similar now in communications, right? We have a larger number of antennas, narrower beams. So again, this is getting closer to radar processing. We have new technological enablers, machine learning, right? Which of course will make things easier. I mean, especially, the resource allocation for this joint system will be very complicated. When we are talking also about sensor fusion, machine learning can also be a very nice tool. So machine learning will help make this joint communication sensing also a reality. And we also have, of course, economic enablers. We have a densification of wireless network, which means that we have wireless signals everywhere that could be used also for radar. And also economy of scale, especially for the wireless industry. Like chipsets are becoming very cheap and hardware is becoming very cheap, which also helps the radar systems. Okay, when we talk about spectrum sharing, there are some existing approaches from the literature. It always started with coexistence, right? Which means, okay, something similar to cognitive radio, where we have two different systems on radar and communication systems. They share the same spectrum, and one of them was primary system, for instance, radar system. The other one tries to see some white spaces in spectrum and space, and we'll use that white space for its application. The problem here, this is not flexible enough, and we cannot offer radar as a service using this approach. They are separate systems. And then the literature started to see two different approaches. We call RADCOM or COMRAD. RADCOM just radar systems, for instance, additional radars. Well, we do some small changes in the waveforms to allow for transmission of data, mostly with a very low data rate. It has some usages, but it's not really efficient for communications. For instance, we can modify the traditional chirps by changing the frequency, by changing the inclination, many other things. The other approach is to have a communication waveform like OFDM. For instance, people are using that with Wi-Fi a lot. Now you can use Wi-Fi signals to detect objects. It also works, but the thing is we cannot offer any guarantee for radar. And this is being done opportunistically. We use the existing waveforms and signals from communications when they are available, so we cannot really control when they are transmitted and if they will provide the desired resolution and so on. So it started with these approaches, and now the research community is evolving towards joint communication sensing, which is really a co-design, right? Which is targeted at efficiency and flexibility. And we either can have a single waveform, or even we can use different waveforms. And then we have a single net layer, which will control the access to the different services, allocate the resources for communication and sensing according to the needs. So that's the important thing. We have to just be flexible. We have to be able to flexibly allocate the resources between both purposes, communication and sensing, depending on what we need at each time and each place. Okay, so again, the idea is flexibility. When we look into future networks, they will serve many different application requirements. So we can think of a single system, maybe even a single cell, which will have several users. Some of them will be doing just communication, maybe some smartphones. Some of them, like vehicles, they will do mostly sensing, but some communication to exchange some control information. So the focus is on sensing. Or we can have robots which are remotely controlled, and they will have both communication and sensing. So again, this flexibility is very, very important here. Right? We have to be able to accommodate the needs of each user, and of course, the users can change in each cell. Right? So there are different approaches on how we do it in cellular networks. We can use what we call network as a sensor. The idea is that the network, the base station, will be our sensor. right? And then using traditional radar terminology, it can be monostatic, where the base station sends out a signal, the signal is reflected by an object, and we measure the reflection. It can be bistatic, where we have, for example, a user equipment, a UE, which sends a signal. The signal will be reflected and will be measured by the base station. Or it can be even multistatic, where we have several receivers, for instance, the signal reflected and detected by several base stations, and the signals are combined by a server which will perform sensor fusion. Right, and we believe that probably all of them will be supported and will coexist in the 6G networks. There are some advantages of both approaches for monostatic and bistatic, and the multistatic is just an extension of bistatic.
So I just have a question.
Yeah, sure. Yeah.
For the previous slide.
Yeah.
So when I was thinking about radar, I was more thinking about monostatic.
Yeah, that's the traditional way.
The traditional way of radars. But my question is how difficult is it to process the signals for the bistatic and multistatic? Is it really easy to do it, or is it really difficult?
I mean, monostatic is easier. That's what basically the next slide. I mean,
okay.
Yeah, because in monostatic, I mean, we have a known reference, a known time reference, so it's easier. But in bistatic, I mean, first you need to know where the transmitter is. We need a reference, right? And again, we need a reference for the signal. And usually we need to have a strong line of sight component that we will use to establish that reference with its time reference, and then we measure the difference from the delay. It's like here we would have here one line of sight, which we use a reference, and then we measure the difference in the time of flight from both sides. So it is more difficult. But on the other hand,
and the second question, sorry,
yeah.
There are some directionality that are not, in my opinion, maybe I'm wrong, are not taken into account in wireless networks. Wireless network, you try to reach a smartphone, and then if you reach it, it is okay. Here you need not only to be able to receive the signal, but to be able to know the direction. Is it easy to implement this in antennas?
Yeah, but nowadays already in 5G we have
we
have beamforming direction antennas, and 6G. Yeah, 6G we will have even narrower beams, and yeah, that's possible. Yeah. But again, but I mean, monostatic radar is easier, as you have asked. The problem is that we have lots of self-interference. That can be a huge problem in monostatic radar. Just to show the problem, I have here one example. Like we have one radar which transmits the signal to 0 dBm with an antenna with 8 dBi, and we have a target which has a radar cross section of 1 square meter, right? Just like a person with 1 square meter, right? And then we have the propagation loss. Have two-way, right? Because the path is at twice as long as the distance. And then in the end, the reflected signal will arrive at minus 124 dB. Just an example. So the target is 50-meter distance. We're using 26 gigahertz and so on. And let's say that we have an isolation of 40 dB between transmitter and receiver. And the signal that's been transmitted, part of it will go the right direction, but part of it, of course, will be leaked to the receiver. Right, so let's say we have 40 dB isolation, which is quite a lot. I mean, this is already challenging to happen. So the self-interference, this leaked signal, will arrive at minus 40 dBm. Okay. The desired signal is minus 124 dBm. So we have 80 dB difference, which is quite substantial. But we might have problems when we quantize the signal, we lose resolution. The receiver may saturate because its power may be too high. It might saturate the long-range amplifier. So this is a big problem, right, with monostatic radar. What people usually do is you can have separate antennas, right, and give them a certain distance to increase this isolation. We can have some special materials, maybe metal materials, which will control this. Or there are methods I'll see later, for instance, if we transmit using chirps, FNCW, the chirps themselves, they can be processed analogically in order to remove the self-interference. But this is one of the big disadvantages with monostatic radar. And we can have the base station, the network as a sensor. We can also have something similar, but they have an UE, the user equipment as a sensor. There are two main disadvantages that. One of them is complexity. As I have mentioned, we have the self-interference problem, but basically requires that we have full duplexing to receive at the same time. This might be doable with a base station, which is expensive. We can afford to have a more complex and more elaborated design. But for the UE, it's probably going to be very hard. So we don't expect to have monostatic radar in the UEs, at least not in handsets or in the short term. But we also have to think that in the future, I mean, user equipment will not only be handheld devices and smartphones. We can also think of front of cars and drones or wherever also as user equipment. And if you have a car, you can afford to have a more expensive equipment, for instance. So in those particular cases, then maybe we can have also monostatic radar for UEs. And the other challenge when you have multistatic is that we will have to exchange the sensing data probably with the network. So the UE will make the detection, right? And it will transmit it to the network. The network will then combine the information from many sensors. And of course, this will require some radio resources and so on. So that's also a challenge. When we think about use cases, I can have many possible use cases. The main ones are in the automotive industry. That's where people are using radar right now. Right? That's what we do towards autonomous driving. We can also think about navigation of drones. But there are many other applications. Right? People are working on human machine interface by having gesture recognition, using radar to detect gestures. There is already one chipset from Infineon which does that. It is already available in Google phones. We can use radar to detect and to count people in indoor environments or even outdoors. There are applications for agriculture to monitor the foliage of different plants, also to monitor the moisture, the soil moisture of plantations. We can use it for robots to safely interact with machines so that they can identify if there's someone close to them. We can monitor vital signs using radar. We can monitor heartbeat and breath rate using radar. We can use it for environmental monitoring to detect floods, rain, toxic gases, insects, or whatever. So there are a very large number of applications. Some are still unknown. I mean, and I believe that once we have this feature available in wireless networks, once we have radar as a service, people will come up with new ideas, with new applications. I mean, we have seen that happen before with localization, for instance. I don't think anyone ever predicted that we'd have Uber and Lyft. That was really someone that came after the service was there. So I really believe that once we have radar as a service, we will have many new applications. But again, of course, we have to be careful. I mean, I think we are given too much power to machines. I mean, they're becoming intelligent, they will have sensors and they will communicate. So the thing is, we need regulation and laws. So this is not only technical problem, this is also a societal problem. One clear example with radars, for instance, now we can already measure heartbeat and breath rate of people, and people are not aware of that. So, and they can even be outside the room. I mean, so we don't even have to be in the same room to perform this kind of monitoring. So we can detect across walls. So I mean, it's really a privacy issue that has to be regulated somehow. Talk about waveforms a little bit. So there have been many approaches in the literature regarding the co-design of so-called dual function waveforms. And we can divide them basically into two areas. One of them is FDM based. like FDM, which is just an extension of the waveform which is currently used for Wi-Fi, for 5G, probably also for 6G. And FDM, pretty good for data, right? It has very high spectral efficiency. It has been shown that it's also pretty good for radar. It provides some pretty good radar detection properties. And we can allocate the resources in time and frequency and even space very flexibly. So it's pretty good, but it has also some disadvantages for radar. As we have seen, monostatic radar requires full duplex. We have transmit and receive at the same time, which can be quite hard to do. We require very high sampling rate. What I mean high sampling rate, I mean that the whole processing is done digitally. So we have really to sample the signal at its bandwidth at least, right? And it also has a very high PAPR. So you also need a large number of bits to sample it. And when we talk about radar, we're talking also about very large bandwidths. We have currently from bandwidths of above 1 gigahertz. So we will have to sample at above 1 gigahertz with a many bit resolution. And that may have prohibitive cost for some applications. So this is a problem. And on the other hand, we have FMCW or chirps, which have been traditionally used in radars. I will talk about this briefly. And the main advantage why it has been used, it has pretty good radar detection properties, but it allows for simple transceiver architectures. Simple, cheap, and efficient, power efficient. But the problem for communications, yeah, we can modulate it, but the data rate probably will be low. I personally believe that we're going to need both, depending on the application. Again, this is my personal view, not Nokia's view. And just briefly about FMCW, frequency modulated continuous wave, also called chirps, because it's when a bird do the chirp sound, it basically just modulating its frequency changes over time. Right? And linear chirps are widely used for radar. They are very efficient. Like if you see the time domain, something like this, or the frequency changes over time. And if you look at the autocorrelation, that's what really matters for radar detection. You see that it's very narrow, so it's very good for radar detection. I'm not going into details here. And also it allows for what we call stretch processing. So right, the idea is that we can easily handle the self-interference, because what we do, we just make a signal in time and frequency, right? We can observe a delayed version of it. And when we multiply both signals, we just measure the difference between those the transmitted signal and the delayed version. And the difference is always constant, so we will observe in the frequency domain just a single frequency here, right? Another one that for itself interferes. So it has two advantages, two good things about doing that. One is that we can just have one DC blocker and we can easily remove this self-interference, just a high-pass filter. This is all doing analog domain, right? And also, if we know the maximum distance that we have, I mean, this frequency here is proportional to the distance. If we know the maximum distance we want to detect, we don't have to sample at a very high frequency, just sample up until the frequency that we desire, right? So we can have a low-pass filter, and we can sample afterwards at a much lower rate than what we would need. So typically the sampling frequency is much lower than the signal bandwidth. So that's why we can have very cheap devices, because we can easily eliminate self-interference without need for complex full duplexer, and we can sample at a lower rate. So that's why it was used. I mean, it can be modulated, but yeah, when we talk about radar detection, we talk about the ambiguity function, which is basically just the autocorrelation in time and frequency. And we see that it has a very narrow autocorrelation time and relatively wide in frequency, which is good, because usually we don't know when we correlate, we don't know the frequency. So we want to allow for a certain frequency offset, right, to account for Doppler, and that can be easily done with chirps. I'll just skip that because of time. So chirps are pretty good. For radar, they can provide for efficient and cheap hardware. They're also good to detect both in time and frequency. But in communication, we usually use OFDM, so we want also to keep on using it for radar. And it has been shown that OFDM signals can be used for data transmission, very high rate, very high spectral efficiency, and also it's good for radar detection. We can dynamically allocate the subcarriers for both sensing and communication. We can even reuse the data subcarriers for sensing if we know them. I mean, this was on a static radar, we know what we're transmitting, we can use it to detect objects, because frequency is the dual domain of the delay. So if we just do an FFT for the frequency response to the channel, we have the delay response, so we know where the reflections are. Right, and if you look into radar properties, like we can also use modulated signals. I mean, it doesn't have to be a reference signal. We can use the data transmission to detect. And if you look at the ambiguity function, it's very concentrated both in time and in frequency, which is good for time, but it has a very low tolerance to Doppler mismatch. And when we talk about radar, we usually want to detect the velocity, the Doppler as well. And how do we use OFDM? The idea is relatively simple. What we do is just do a channel estimation. Right? We know what we are transmitting. Right? So we just do the typical OFDM processing. I'm not going to go into details here. In the end, we have the received signal after the FFT. We just the transmitted data multiplied by the channel matrix. So since we know the data, we just divide by it and we get an estimate of the channel. And if we get an estimate of the channel, as I mentioned before, that's an estimated frequency domain. Just do an IFFT, then we get an estimated time domain. So we know where the main reflections are. We can use it for radar detection. So it's relatively simple. Again, the only constraint that the maximum delay must be less than the length of the cyclic prefix. So it works very well. But as mentioned before, it has a drawback that's not very suitable for high Doppler environments. We know OFDM is very sensitive to frequency offsets. What we can do here, we can have a larger subcarrier spacing, which is already done in wireless communications, but of course that comes with a higher overhead. So it's not always the best solution. And there has been many new waveforms that were proposed, like from a chirp division multiplexing, where the instead of subcarriers, we use different chirps with different frequencies, or OTFS, we talk about time frequency space. So they are all FFT based, so they are similar to OFDM in a sense. So they can be implemented with OFDM, with the precoder before the OFDM, so we can also implement those waveforms. And they can be more efficient when they have high Doppler. So these waveforms are being considered maybe for 6G. And again, the problem here, as mentioned before, is that we need full duplexing. If we're doing monostatic radar, we have to transmit and receive at the same time over the full bandwidth, and that's it can be quite challenging. Just one slide to show here, we have performed some simulations, right, with both OFDM and FMCW and self-interference. We have here the traditional ROC curve. Right, we have the probability of false alarm and the probability of detection. Ideally, we have very low false alarm, very high detection, so we'll be close here to this one as possible. And we can see here, for instance, considering the same isolation, 30 degrees, right? The relation between transmitter and receiver. We see that OFDM performs much worse than FMCW because, again, it's much more sensitive to self-interference. So we really need full duplexing with OFDM. And again, this can be a challenge. So some challenges that you can see here. I mean, there is no one size fits all solution. I mean, depending on the application, depending on the hardware, it might be better to use OFDM or FMCW, and with different parameters. Again, what's different from traditional radar, that here now in 6G we will have many different applications. We're not making a radar for automotive users. We're not making a radar for, I don't know, for weather forecasts. We want to have a system that can support many different radar applications and communication applications. And apart from this, we will have many different devices. I mean, we cannot compare. Again, we can have full duplexing maybe on the base station, but not on handsets. Like we have limits in terms of picture average power ratio, amplifier power, amplifier efficiency, and so on. One thing that we can consider is, I mean, OFDM is really good for spectral efficiency, but we don't always need spectral efficiency, particularly in the future. Let's say we will have bandwidths of a few gigahertz. And why do we want to transmit 20 bits per second per hertz? That might be what always be needed. Right? So if we have a couple of gigahertz, it might be enough to transmit to 0.1 bits per second per hertz. We'll still have 100 megahertz or more. Sorry, 100 megabits per second or more, which is usually more than enough. So that's something to consider, because again, FDM is good for spectral efficiency, but it's very bad. I mean, it's relatively bad in terms of energy efficiency. Right? And again, depending on the hardware, we don't always can do full duplexing and sample at a high rate. So we think that we need a flexible filter layer, a flexible MAC, which will understand the different possibilities in terms of both communication radar and allocate the resources accordingly. It can be done, for instance, in the time domain, or something hybrid. Instead of having this block motivation screen like FDM or just FMCW, we'll have something hybrid. In some subframes, some slots we use FMCW, some slots we can use OFDM or something similar, depending on the needs. There are some challenges for this hybrid waveform. First, we have to understand the requirements of different applications. In terms of many KPIs, now we have not only the communication KPIs, right, which are well known. Now we also have to consider the radar KPIs. Right, and QoS for radar is still a nascent topic. I mean, nobody really knows how to define quality of service for radar. Apart from that, we have to consider the hardware limitations. Right? Including energy consumption, what's your ADC capable of, and so on. If you have full duplex or not, and then choose the waveform. Right, and of course, as usual, engineering requirements can be conflicting. Right, so for radar, we want high bandwidth, but that will demand a more complex transceiver. If you want to measure Doppler resolution, and we want to have a very high Doppler resolution, we need long frames, but that will impact latency. So we always have those trade-offs. And if you look into an example, if we have, let's say, a street crossing, and we have many cars coming from different directions. We have radar in those cars, we have radar in the infrastructure, they are communicating among themselves, they are collaborating. And we want to have one single KPI. We want to maximize the probability of detecting those pedestrians here. That's the KPI. Right? And then we have to design our system taking into account all those challenges. We have to manage interference among all the different transmitters, both in terms of the communication and radar signals. Some of them will be monostatic, some of them will be bistatic. So we have to coordinate it, take into account what they are capable of. We need to exchange information, and then we have to decide, okay, what kind of information are we exchanging? Because part of it will be conveyed also wirelessly and take up wireless resources. So do we want to transmit just a local decision? I mean, I see it aggressor, or do you want to transmit the raw data, which will be centrally processed? Okay. So there are, of course, trade-offs in all these options. And of course, in the end, we have to allocate the radio resources to these radar and communication links. So it's a large challenge. And if we change our objective, if we're using the same equipment, we don't want anymore to detect the pedestrians, but we want to build a digital twin of this environment, then the requirements will be completely different. So that's the challenge, right? Because we have to allocate the resources, taking into account many different aspects, and the KPIs will be widely different depending on the application. How's the time? But
20 minutes, question included.
Okay. So maybe some 5 minutes more. So what we need to know, I mean, in such a scenario, we will have several devices. We have to know for each of them which are the supported waveforms, if they have duplex or not, what's the sampling rate, what's the radar and communication capabilities of each of them. We have to know if we know the resource allocation, time, frequency, space. And if we know that, we should be able to derive the service parameters, which are required for radar and for communication. For radar, we have radar resolution, estimation accuracy, detecting probability, false alarm rate, and and so on. And for communication, we also have a set of APIs. So we want to know that. But and once we know that, we want to do the opposite way. Right? It's like the first step is to know how to derive those. Knowing how to derive those, we want to do the inverse. It's like once we have a set of parameters, like what are the application requirements for both communication and radar, we have to know the devices that we're dealing with, and we have to know how the network is operating, what's the SNR, what's the network load. And based on that, we should be able to choose for each device some parameters like what's the waveform, are you using FDM, are you using FMCW, what's its numerology, how are you going to configure the hardware for the sample rate. We can also change the sample rate and the ADC resolution dynamic, for instance. That's one idea to save power, for instance. Whether we have full duplex or not, again, we can also turn off full duplex because it typically consumes lots of power. We should be able to adjust the field of view, the beam width. So again, based on all these parameters, right, we should be able also to adapt our hardware the best way that we can. I mean, there are many research challenges. I'm not going into details on all of them, but if you look into the literature, most of the available work is on physical layer. Right? It's basically on deriving waveforms and signal processing algorithms for radar and communication. So that's maybe 90–95% of all the papers. And still there are lots of challenges, both in terms of RF chain, how can we configure the RF, how can we reuse the same front end for both radar and communication efficiently. For instance, what's the impact of those hardware impairments? I mean, hardware will never be perfect, and that's what people usually consider in papers, but real life is much more complicated. We can think of using reflective surfaces. How can they be leveraged to improve radar processing, and so on. Again, there are many open challenges in the physical layer, and there are even more challenges if you move up the protocol layers. For instance, MAC and RLC will need new signal protocols for radar. Again, we see very few papers on that topic, but people are still already working on that for standardization. Again, the problem that I mentioned about resource allocation, we have to allocate resources. Yep.
When you use protocols for radar, would you do something like, I don't know, CSMA, where you would try to protect a given beam from interference? Or so what do you mean by?
Yeah, I mean, really signal. I mean here is that you have to say, I want to perform sensing, so I have to tell the base station, okay, now please send one sensing signal. That's what I mean. It's not a MAC protocol. I mean signaling.
Oh, okay.
Yeah. But of course, we also need a MAC protocol. But
okay.
Yeah, I think we will keep on using OFDMA for the future. Okay. And again, how to allocate the resources. That's a very hard challenge. I mean, there are too many factors to be taken into account. We will have probably increased interference because we have more systems. We can use dedicated signals, or we can use opportunistic signals, use what's already there, or we can design new signals. Radar may require multiple bands if you want to achieve a high resolution, so we have to control those multiple bands together, and so on. We have latency, which is an issue which so far hasn't been considered yet, but for some applications, especially for collaborative radar, latency can become a problem. And again, when we move to the networking layer, end-to-end performance, there are still many challenges. We are having some discussions, for instance, on different QoS for radar. I mean, nobody really knows. Because there are so many different applications, but we want to have something really which is standard for all different applications. Nobody really knows. Some information, if we have fusions, we'll exchange part of information. Wireless is partly using cables among base stations. And again, which information are we going to exchange? Or just local decisions, raw data. And that, of course, will impact communication needs. Is the current front haul fleet, which was designed for communications, also adequate for radar? We don't really know. Okay. There are many questions. This is very important to privacy and integrity. How can I've already talked about privacy? How can we make sure that we are only sensed when we allow? stuff to be sensed, and how can we be sure that the data that we sense is the real data, that nobody is tampering with the data and spoofing your data signal and so on. So there are many open topics for research, which is good for us, so it will keep us busy for a long time. Right, and there are other challenges. For instance, we still need a unified information theoretical approach to be able to analyze the fundamental limits, fundamental capacity limits of a joint system. There is no channel model for simulation, for instance. We have channel models for radar, channel models for communications, but they do not represent the same thing. That's what we need, something that represents the same environment. Just to finish the presentation, talk about very briefly about some standardization activities on the topic. At Nokia, we work with standardization. I am in Nokia standards. So we can see some activity already in Wi-Fi, 802.11bf, what they call Wi-Fi sensing. But there is already a draft, but the final standard should be ready by the end of 2024. Wi-Fi is the progress is very high there. Also UWB. UWB is currently being used a lot for localization, for indoor localization. It's very precise. And they are working on a new amendment, which is 802.15.4ab. They call it UWB Next Generation, which will also support sensing besides localization.
Just what does it mean, UWB?
It's ultra wideband. For personal area, local area networks, and again, it's currently used mostly for localization. Provides very, very precise localization. And of course, it's CDPP. That's where Nokia's interests lie. Sensing will certainly be part of 6G. Sorry, let's mistake here. Sensing 6G system will be designed with native joint communication sensing. That's almost certain. Probably still using OFDM, at least at the beginning. We might have different waveforms after a while, but industry wants to keep using OFDM for a long time. And we might see something already in release 19, which is 5G advanced. Just to have an idea of the timeline for 3GPP. Right, so release 19 should be ready by mid-2025. We are already discussing some use cases and application. So we might have already some sensing supporting 5G advanced. It's also because, I mean, 3GPP has to follow what Wi-Fi is doing, right? If Wi-Fi has support for sensing, and yeah, 3GPP will have to provide the same. It's really a race. And then again, 6G specs, right, will be by release 20, release 21. They will certainly include sensing as a service for wireless networks. And we expect to see the first commercial deployment by the end of the decade. Okay, that concludes our presentation. If you have any questions?
Thank you. Any question in the room?
If you take, I mean, in your set of questions, assume you have initially a bandwidth, right, in size. I mean, can one answer the question? Assume you want to do, you're on this car setting where you want at the same time to use sensing, radar sensing and communication. Can one answer the question, is it better to use the same band for the two operations, or is it better to separate that into sub-bands and do sensing on one side and communication on the other part of the band?
I mean, from the signal processing point of view, it's good to have them both together, I think. Yeah, because you can use the communication signal for sensing anyway.
Right.
Yeah.
But in terms of efficiency, assume you have criteria like spectral efficiency for the communication and the probability of detection for whatever scheme you said it's very difficult to have QoS, but let's say
Mhm.
you have a certain scenario that you want to detect certain things. So can one answer this question of what is best in terms of if you take an aggregate of these two
Yeah.
metrics?
No, I think it will always be better to do them both together because no, I think it will always be better to do them both together because or else you are wasting power, right? Because you are already transmitting some power for communications. And if you can use it for sensing, why not? You can do some interference management, but things get complicated. That's
Okay.
what I mean. I mean,
Okay, so if you can control interference, then you
Yeah.
you will win for
Yeah.
sure, right? But
Yeah.
then if there is an increase of complexity, in terms
exactly.
of,
Yeah. Yeah.
managing the
Yeah.
right. But if you treat interference as noise, then it's not clear, right?
That's not clear. Yeah. Yeah.
Another question about this. So you alluded to this very interesting information theoretic limitation, but assume you have a source, you want to communicate to this thing, and you want also to sense, right?
Mhm.
Something. Does one know? It looks like a broadcast channel of some kind, because you have to talk to yourself, perhaps,
Mhm.
as the receiver
Yeah.
antenna of your radar and listen. So what does one know in terms of capacity for this very specific sensing communication problem?
I mean, I'm not an information theory guy, but I know people working on that problem. Again, I've seen the reflection as a broadcast channel, but the problem I see is that the object itself is also unknown, right? So how do you?
There is no code book, right? Or
Yeah,
perhaps-
yeah, exactly. I mean, the object can be anything. I mean, it can be, and even the same object depends on whether it's facing one direction or the other direction. So it's
yeah.
so the information that it has is also random. So I don't see it as an easy problem because it is not exactly like communication. You can, if you have an object that we know that it's radar cross section, then you can perhaps model it as the broadcast channel. But yeah, again, real life is not like that. Real life is, yeah.
Thank you.
Daniel?
I was wondering about how this joint network could be planned, because just to very down hint of what I meant, is if you are in the communication part, you may want to have a basic MIMO and take advantage of reflections and things of that sort. If you are doing a radar, you may try to avoid reflections. So the position of your cells, of your antennas will be in the same place.
Yeah.
So how can you plan such a joint system?
That's a good question. I don't know. I mean, I suspect that the networks will be planned for communications. That will remain the main service for a long time, and people will do radar on top of that. Right? That's how I see it. But you're right. I mean, that's will also be a challenge. Yeah?
Question on the bridge? Other question in the room? So thanks again.
Okay. Thank you very much.